Hi everyone, welcome to Differential Calculus. Today we explore lesson 4.3, the derivative test. There are two of them, and they are very useful to sketch curve. Number one, the first derivative test, increasing or decreasing intervals. We can use the first derivative to do that. If f prime x less than 0 on an open interval I, then f is decreasing. That is, it has the downhill curve on the interval I. And if f prime x is greater than 0 on an open interval I, then f is increasing uphill curve on the open interval I. We also use the first derivative test to find the critical number and the local min max. If C is a critical number of f, and if f prime x changes from positive to negative at C, then fx has a local maximum f of C. If f prime x changes from negative to positive at C, then fx has a local minimum fc. If f prime x does not change sign at C, then fc is not a local min or max. Okay, let's take a look at some example. Here come example. Analyze each curve to determine the intervals of increasing or decreasing critical numbers and local min max value. So let's take a look at A. We have this curve right here. From the definition, the function is increasing as long as the derivative is more than 0. Derivative is slope of the tangent line. So all we have to do is look at the tangent. Look at the tangent line here. Look at this tangent line here. They all have positive slope all the way until the local maximum. So f is increasing on negative infinity to negative 2. And then also, if you look at from 4 to infinity, right? Slope of the tangent line is positive. Right? 4 to infinity. So that means from negative 2 to 4, check out the slope of the tangent line here. Yeah, it's negative. And so that is where the function is decreasing on. Negative 2 to 4. We have two critical numbers. One is at negative 2 and the other is at 4, because the slope of the critical number is 0. Right? Just a flat line. X is going to be 2 and 4. Okay. Local minimum f of 4, which is negative 3. Local maximum f of negative 2, which is 3. Pretty cool, huh? So similarly, you can do B here. Have a different graph. Right? F is increasing on. Let's take a look. Well, the function is increasing whenever the slope is positive. Positive, 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 positive. All the way up until this point here. This is when the slope is 0. And then it is positive, positive, positive. Yeah. So f is increasing on negative infinity to negative 1. Negative 1 2, 3. And then decreasing when it has the negative slope. Yeah, so that is from 3 to infinity. Critical number occur when the slope is 0. So we have 2 of them. One right here at x equal -1, and another one is at x equal 3. The local minimum, well, we don't have any. Yeah. So it's none. Local maximum, there's 2 of them. Actually, it's only 1. Because at x equal -1, the slope of the tangent line is 0. And the function does not change from increasing to decreasing. So there's only 1 local max. And that is f of 3, which is 4. Theorem. If a function has only 1 local minimum or local maximum value, then that value is the global minimum or the global maximum value of the function respectively. This theorem is pretty useful in sketching parabolas and also in the later section when we study application of derivative in optimization. A parabola fx equal ax squared plus bx plus c. So I mean f prime x is 2ax plus b. And if we set this equal to 0, then x is minus b over 2a. Yay. We have only 1 critical number. And this critical number here can either be the local minimum or local maximum, depending on the change in the derivative. And if it is a local minimum, then the parabola will look like this. And if it is the local maximum, then the parabola will look like this. Pretty cool, huh? So in order to sketch the function precisely, we need another information. No? So far, we know that the derivative can only tell us whether the function is increasing or decreasing. But how do we know whether, let's say, if it is increasing, right? Is it increasing this way or this way? Yeah. Which way? And same thing for the decreasing. Is it decreasing this way or this way, from left to right? Well, we need another test to determine how the function is increasing or decreasing. And that is the inflection point and the second derivative test. Definition on inflection point is a point in which fx changes its curving or concavity. To find the inflection point, we set the second derivative equal to 0 and solve for x. The second derivative test. If the second derivative is less than 0 on an open interval I, then the curve fx lies below or with tangent line on I. This tells us that fx concave downward. Let's take a look at the slope of the tangent to see. So we say that, oh, look at this here. That is the tangent line right here. Sketch another one. And right here. As you can see, the curve lie below the tangent line. So I mean, it is concave down until we reach some point right here. And this point is called inflection point. After the inflection point, look at the function. It is above the tangent line. So that is when we have a concave up, no, concave down. It looks like from this graph here, intervals go from negative infinity up to the inflection point. Let's say C right here, up to C. And concave up, let's call it Fx there. From C to infinity. And for the concave down, the shape look like this. Sad face. Concave up, opposite. Smiling face. Thank you for watching. I hope you found the content useful. See you in the next video.